Welcome to week 9, iterative correctness. Last week we talked about how to prove correctness of recursive programs. Let's see what happens when it's not recursive but it has a loop somewhere in there. Perhaps we'll run into one of the two types of programs in this world. Those that halt. So a brief review of correctness. A program takes an input that is supposed to satisfy a precondition, and provided it does, returns output that satisfies a postcondition. Both of these are predicates, and a program is only correct if and only if, for all inputs, the precondition being true implies the postcondition is true. Again, review, let's look at what happens for recursive code. First off, we need a way to estimate what the input size should be, and then we will prove that the precondition implies the postcondition for all the paths that we could go through. For the base cases, the paths that are taken by the smallest inputs that we can get, we can just check them directly and usually figure out what's going on. Anytime there is a recursive call, we need to use our inductive hypothesis. The recursive call on a smaller input that satisfies the precondition will also satisfy the postcondition. And so we just need to show that the original function call satisfies the postcondition when it's given that result. Now, for iterative cases, things are different. With recursive programs, we know the exact sequence of steps each program path will take, and so we can look at them directly because we know which lines of code are going to be run in which order. With loops, you don't know the exact sequence of steps anymore. It's harder to tell because you don't know how many iterations of the loop will occur, and you don't even know if the loop will terminate. Maybe it's an infinite loop. So we're going to use two things to help us with this. Invariance to tell us that the code is going to be correct if it terminates, and variance to tell us if a loop will terminate. And both of these combined will give us a full correctness argument for a loop. So first off, we need to talk a bit about some terminology. Consider some code that looks like this. While C, we have S, which is to do some stuff. C in here is called the loop guard, is a condition. So like I is less than N, for instance. And this is to actually ensure that you are able to go into a loop and run the code in it, or if you're going to skip over. S in here is called the loop body. It is a sequence of statements that are run in sequential order without any confusion with regards to which is the order that they're going to go in. Now, given that a program contains a loop invariant is a predicate defined based on variables and constants participating inside the loop that satisfies the following. First, it needs to be true before the loop runs for the very first time. If it's not, the whole thing is kind of bogus. Secondly, if the loop guard is true, assuming the loop invariant is true at the beginning of the loop, it remains true by the end of the loop. So there might be some variables that switch values in the middle, but by the end of it, the loop invariant still must hold. So here's another example, a piece of code that does division by 3. And so the postcondition here is to return the quotient of division of n by the number 3. And you can see that this looks pretty similar to the division code that we had from last time, just this time it's using a loop instead of using recursion to essentially, cut 3 off of it over and over and over and increment the quotient. The same way that the code worked from before, this time just with a loop. So let's see how we have to do things a little differently here. So firstly, we need to come up with a loop invariant. And so I've proposed one here. You may be able to come up with other ones that might possibly be equally good. However, these are definitely essential ones that we're going to need for things to work out. So the loop invariant, I'm going to define in terms of n, the input size, q, which is a variable that's inside the code, and r, also in here. And what I'm going to say is that r, our remainder, is greater than or equal to 0, and our value of n is strictly equal to 3 times q plus r. Now, before the loop occurs, can we assure that this is true? Well, at the beginning, q is 0 and r is n. So is r greater than or equal to 0? Well, yeah, it says so by the precondition, because r and n are the same thing. They're greater than or equal to 0. How about n is 3q plus r? Well, q is 0, so we just have n is r, and once again, we know that's true. So everything is okay before the loop runs. Now what about while it's going? Well, let's assume we're inside an arbitrary iteration of this loop. R is greater than or equal to 3 because the loop is still going, and our invariant is true at the beginning. Well, the variant's true at the beginning. What's going to happen at the end? By the end, we're going to have a different value of q. Let's call it q prime. What's it going to be equal to? Well, it's going to change to q plus 1. How about r prime? R prime is going to change from r to r minus 3. Okay. Now let's go back and look at our loop invariant and see if things are still correct. Well, In terms of our n is 3q plus r, well, let's see what 3q prime plus r prime is. Well, if we replace q prime with this formula and r prime with this formula, we get 3 times q plus 1, or 3q plus 3, plus r minus 3. And this 3 and this 3 cancel out, and we're left with 3q plus r, which remains true. So this part of our loop invariant, the second half, is still good. How about the first half? R is greater than or equal to 0. Well, since r is greater than or equal to 3 because of our loop guard, r minus 3, which is r prime, is also greater than or equal to 0. So our predicate holds not just for p of n, q, and r, but also for p of n, q prime, and r prime. And that completes our proof using the loop invariant. And you can call this a proof of partial correctness, because so far there's one very important thing we've yet to prove, but we have shown that these specific facts will hold true for arbitrary iterations. So where is this taking us? Well, the whole point of using this loop invariant is to show that when we reach the end of everything, we can use the loop invariant to show the post condition has been satisfied. So really, we're not actually done our partial correctness yet. We want to use the invariant to show us that the post condition is held. That will complete our partial correctness. Now, here's our invariant. R is greater than or equal to 0, n is 3q plus r. If the loop is terminated, that means this condition must be false. In other words, r can't be greater or equal to 3, therefore r is less than 3. According to our invariant, n is 3q plus r, and r is greater or equal to 0, or you could say 0 is less than or equal to r. If we combine the fact that the loop has been terminated and the loop invariant, we have, n is 3q plus r, and we also have that 0 is less than or equal to r, which is less than 3. And it turns out this should look familiar to you, because this is the exact formula we used last week to talk about what the remainder is for doing division by, in this case, specifically 3. So by the Euclid's theorem that tells us this is what we use to determine the quotient, the post condition has been satisfied. Now, partial correctness is cool because it does help us figure out that our program will be correct when it gets to the end. But a correct program must terminate. And loop invariants don't really tell you anything about will the loop actually finish. Any invariant that's true when the loop is finished will be true, but if you look at code such as this one, which is supposed to calculate the sum of naturals, and it just has a while true loop, basically, it never terminates, so it's not correct. Which means we need something else to ensure that our code is entirely correct, not just partially correct by the nature of the loop invariant helping us with the post condition, but also that it terminates. So to prove termination, we need something called loop variance. So bear in mind, this is not the same as invariance. Invariants are facts that help us for the post condition. Variants are things that are going to change to help us show that a loop will terminate. The way that we do this is we pick a loop variant v, typically should be an integer, that has the following two properties. First off, every iteration of the loop guarantees that v is strictly decreasing. It is never going to stay the same or go up. Secondly, the combination of the invariant and the loop guard together imply that v is greater or equal to 0. In other words, you have some natural number v, which is constantly going down, and it started off by something being greater or equal to 0. If it decreases all the time, that means that eventually it will go below 0, meaning that at some point the loop will actually have to terminate. So let's start looking at our first practice problem here. Here is the code that calculates an average of a list of numbers. Here's the code. Precondition, it's a non-empty list of numbers, and the post is it returns the average. What is a correct invariant for this? Sum is greater or equal to 0. I is between inclusively -4 and the length of a plus 2. The sum is greater than or equal to a of the index I, are more than one of the above correct invariants, or none of the above. Now, it turns out that while some invariants can be true and can be sometimes proved about a loop, not all of them are useful. And really the trick to doing correctness for iterative programs is finding it useful invariants for a loop. So here is the average code that I just had up. And what we're going to look at is a specifically useful invariant for this loop, which is the following. The invariant is based on I and the sum, and so I is going to be between inclusively 0 and the length of a, and sum is going to be strictly equal to the sum of a of k from k is 0 up to I minus 1. So this invariant means three things. I is at least 0, it's at most the length of the list, and sum is basically the sum of the first I elements of A. Now, first off, we want to do partial correctness of the program with our loop, and partial correctness because we haven't shown yet that the loop is going to terminate. And this is, again, induction. We start with a base case. The invariant is true when we reach the loop. Induction step, assume that the invariant and the guard are true for some arbitrary iteration, which is kind of equivalent of doing our induction hypothesis on p of n minus 1. We then show that the invariant holds true after one iteration of p of n. Finally, we check the post condition. We argue that the invariant and the negation of the loop guard together let us conclude the program's post condition. And we use the negation of the loop guard because that tells us what happens after we've exited the loop. In order to be out of the loop, what must be true of the variables that are declared in our code. So let's start off looking at our base case. We want to argue that the loop invariant is true when we reach the loop here. So when we reach the loop, I is 0, the sum is 0. All right. 0 is less than or equal to 0, which is less than or equal to the length of A, since A is a non-empty list of numbers, so that's okay. And then we have, what's the sum of the first, well, none of the numbers of A? Well, it's just 0. So both of this part is true. Great, base case is done. All right, now let's assume that the invariant and the guard are both true at the end of an arbitrary iteration. We want to show that the invariant is true after we go through an iteration. We'll use here subscript 0 for before and 1 for after. If you prefer to just use the letter and then the letter prime, that's okay too. We'll keep it with 0 and 1 so you can see before and after. So two things we're assuming. First, assume the invariant is true for I0 and sum 0, and we assume the loop guard is also true. In this case, our loop guard is I0 is less than the length of A. So now we need to prove that the invariant still holds for I1 and sum 1, and we're going to do these two separately. So let's first off start with 0 is trying to prove that 0 is less than or equal to I1 less than or equal to the length of A. From the loop body, we know that I1 is I0 plus 1. It's just directly calculated there, which means we need to prove that 0 is less than or equal to I0 plus 1, which is less than or equal to A. Now we know the first part of this, the 0 is less than or equal to I0 plus 1 is true because we already know that 0 is less than or equal to I0. That's part of the loop invariant. We know that's true. The second part must be true specifically because I0 is less than the length of A. If it wasn't, we wouldn't be in the loop anymore. The loop condition specifically is I is less than the length of A. So if I0 is less than the length of A, I0 plus 1 is less than or equal to the length of A. Okay, now how about the second half? Here we're looking at the summation of the first I terms that's supposed to give us the sum that we've gotten so far. So based on the code again, the sum here is going to be the previous sum plus the I0th term. I0th term, yes. And I1 is going to be I0 plus 1, just like we saw before. So our summation is the previous sum plus the new term. Which, from our loop invariant, we get this summation, k is 0 up to I0 minus 1 of AK. And we add A of I0. That's literally what happens in our code here. We add that term in. If we combine these together, we remove the minus 1 up from here, which gives us I0 at the top of our summation. And we know that based on this, I0 is equal to I1 minus 1. And this is exactly what we wanted to show. So we've proven both parts of our invariant, which completes that induction. Now, okay, we know that our loop invariant is going to be good while we're going through the loop. Now we need to conclude the post condition based on that information. So combining the invariant and the negation of the loop guard, what do we have? So the first two parts here are from the loop invariant. And the last part here, if I is not less than the length of A, that means I is greater or equal to the length of A. Well, here's something that you should note. If you look at the third part here, I is greater than or equal to the length of A. And the first part over here, where I is less than or equal to the length of A, the only way for this whole thing to be true is if I is the length of A. Well, if that's the case, we have I is the length of A, and we have the sum here from k equals 0 up to I minus 1 of AK. that is the sum of all the elements of A, because I is the length of A, and I minus 1 is the final index that we have, right? If your list has 10 elements, what's the last index? It should be 9, so you're summing from 0 up to 9, which means our sum is the sum of all the elements, and our code is going to return the sum that we've calculated divided by the length of A, which is the average, and we've met our post condition, so you can celebrate just like Freddy over here. So here is your overall quick recap of everything that we've done here, proving partial correctness of a program with a loop. It's induction in another form. The base case, you just show the invariant is true when you reach the loop. This is usually pretty straightforward. For the induction step, assume your invariant and your guard are true at the end of an arbitrary iteration, so that's our p minus 1 for induction hypothesis. Show that after an iteration, the invariant still holds for the new values of each variable that changes. Check the post condition. If you have the invariant holding true the whole time and the negation of the loop guard happens, combine those to figure out what must be true for the post condition. And usually this means you need to phrase your invariant in such a way that there are restrictions on the values of certain variables so that you can combine it with the negation to determine what the exact value of a variable will be at the end of it. And then proof of termination is the second part. So how do we prove that this terminates? Well, we need to pick a variant, and the variant needs to be a natural number, so it needs to be greater than or equal to 0, and it needs to be a whole number that is going to be decreasing over time. So what should our invariant be? You might think, well, maybe it should be I, because I is changing, but that's no good, because I is always going up, which is not great. How about we consider the following? Length of A minus I. Is this a good variant? Well, it decreases on each iteration because I is going up, so length of A minus I is going down. That's good. Now, can we ensure that it's going to be greater or equal to 0? Well, from the invariant, we know that I is less than or equal to the length of A, meaning that the length of A minus I is greater than or equal to 0, and this is exactly what we need to have for a variant, so this is a good choice. Let's finish off with a few last practice problems. So here's some code that returns A times B for multiplying here, and here's all the code that's there. What is a correct invariant for this code? If x is even, then x times y is unchanged. X times y is A times B. X times y is A times B plus the total. More than one of the above are valid invariants, or are none of the above valid invariants. Now, continuing with another question, given the same code, what's the best variant for this? Is it x, x times y minus y, x times y minus x, or x times y? So, final problem, here is some mystery code. It does something. Maybe you want to try it out for yourself. And consider A plus 5. Is A plus 5 a variant for the loop? Is it not a variant because it could be less than 0, or is it not a variant because it's not guaranteed to decrease? One of these options is true.